Hello, my name is Frank Liu, and I'm presenting spatial audio-empowered smart speakers with Xblock, a post-adaptive crosstalk cancellation algorithm for free-moving users. Smart speakers have seen rapid adoption over recent years. Imagine the possibility if a network of these Internet of Things-enabled speakers was capable of delivering spatial audio to users. Spatially placed virtual sounds could create sounds in midair, or grant audio to objects that would otherwise be unable to produce sound. For example, a user could locate items through spatial audio guidance and/or interact with objects through auditory response. How we perceive where sound comes from in the physical world comes from a combination of two primary auditory cues. The first is interaural level difference, which is the difference in time between a sound reaching one ear and the other. And the second is interaural level difference, which is the difference in sound pressure or level that reaches each ear. You might have heard audio that sounds like real life watching a YouTube video or playing video games. Binaural audio can create 3D sound effects that simulate sound as if it's being heard live using the ILD and ITD cues. It creates these effects by adjusting the amplitude and delay of the left and right audio channel in each ear to create the illusion of sounds coming from different directions. Binaural audio sounds best via headphones because the left audio channel is delivered directly to the left ear and the right audio channel is delivered directly to the right ear. Playing binaural audio over a pair of loudspeakers, however, is challenged by crosstalk, where audio from the left speaker reaches the right ear and the audio from the right speaker reaches the left ear. Due to the intermixing of audio channels and ears, crosstalk reduces the presence of the ITD and ILD cues, thus destroying the user's perception of audio spatialization. Crosstalk must be cancelled to enable spatial audio over loudspeakers, resulting in audio channels that are properly delivered to the user's ears. We describe our novel algorithm called Xblock. Xblock allows users to experience real-time spatial audio by pre-processing sound signals through time shifts and gain changes based on the head and speaker pose. When audio from the loudspeakers reaches the user's ears, the binaural spatialization ILD and ITD cues are preserved. Most notably, Xblock supports crosstalk cancellation for dynamically moving users, where a user could be walking, ducking, or jumping around in a physical environment for a loudspeaker pair system. Conventional methods of static crosstalk cancellation use filtering via inverse crosstalk transfer functions or recursive filtering. However, this only works when the user is perfectly in between two speakers, and this limits the user's range of motion. There have been many related work which uses loudspeaker arrays to render the spatialized audio effect. Speaker array system techniques are generally using more than two speakers, and these are established methods of generating spatial audio. However, these techniques are expensive in cost, setup, and computation, making them impractical for at-home listening experiences. There have been recent work for dynamic crosstalk cancellation which involve updating an inverse transfer function based off the user's HRTF from a filter bank. However, these works incur a noticeable delay for the user or require an intensive setup in updating a room response model in addition to the filter banks. There have been existing work implementing a low latency dynamic crosstalk cancellation designed specifically for a cave environment. While it's very easy to walk into a cave and experience spatialized audio, these environments are not something one can simply bring into their living rooms. There are alternative audio methods which can give spatialized audio to a user. Acoustically transparent headphones are a viable alternate solution to providing spatial audio to the user with additional hardware. Examples include Bose frames, bone-conducting headphones, or Apple AirPods Pro with transparency mode. Authors of Digital Ventriloquism built a device that modulated a 40 kHz ultrasonic signal, and upon collision with an object, the signal would demodulate to audible frequencies, and thus the object would be the origin of the sound. Compared to other work, Xblock supports dynamically moving users. Xblock is implemented as a low-latency software solution, and is easily integrable into existing systems without too much additional hardware or setup. From a high level, Xblock is an algorithm that allows users to experience real-time spatial audio by pre-processing sound signals through time shifts and gain changes based on the head and speaker pose. In our algorithm, we do make a couple assumptions. The first is that we assume an ideal multipath sparse environment. Second, we assume that there is a direct path for the audio to propagate from the speaker to the ear without any obstruction in between. With all that said, let's dive into the algorithm and see what these time shifts and gain changes look like. To start us off, we have a goal of what our left ear and right ear hears to be equal to the input left and right audio channels with some delay, capital T. We create equations representing what the ears would hear in physical space, a sum of the speaker outputs with its respective decay and delay changes. Based off our ear models, we solve for the speaker equations in relation to the input channels. Then we get to our Xblock algorithm. After expanding equations 4 and 5, we get to equations 6 and 7. These show how the input channels should be modified. When we plug our Xblock speaker equations back into our ear model function, we return back to our original goal, to have what our left and right ear hears to be equal to the input left and right audio channels with some delay, capital T. Further details can be seen in our paper. In order for our Xblock algorithm to work properly, we need the proper input parameters. To obtain these parameters, we characterize the gain, decay, and sound delay of the speaker audio as a function of distance. To characterize the gain and decay, we use the inverse square law for sound to create a linear fit of distance to decibel level. We recognize that in reality, the sound sources do not radiate evenly in all directions, and room reverberations impact the sound distribution. However, we make this assumption about the behavior of sound in order to generalize the implementation of our algorithm. In order to find the proper delay values, we divide the distances of each ear relative to each speaker by the speed of sound. With regards to the implementation, we integrate the Xblock algorithm into the Resonance Audio source code, which builds to a Unity Audio plugin. Resonance Audio is an SDK that generates high-fidelity spatial audio by simulating audio propagation and interaction with human ears. In Unity, the head and speaker poses determine the gain and delay input parameters, which are sent to the Xblock plugin every frame update. Notably, Xblock processing is lightweight and able to generate audio with negligible latency. On a 2.3 GHz MacBook from 2019, the processing took on average 105 plus or minus 31 microseconds over 200 runs. The plugin also gives users the option to bypass Xblock processing. We created two systems, one for VR, which we use to conduct live recordings to capture the ILD and ITD cues, and one as a prototype IoT system using the laptop as the main hub with two connects to capture the object and body pose. The laptop then sent audio to our smart speaker, which was a networked Raspberry Pi with speakers. Each system consists of a virtual environment which spatial sound synthesis occurs. In our implementation, that virtual environment was Unity. Each system also contains our Xblock plugin and some way to get the head or speaker pose, either through a VR tracking library or a visual tracking library. With the VR implementation, we used it to capture the ILD and ITD cues. We captured live recordings on a physical binaural dummy head microphone. Audio played from the physical speakers, and we captured the audio via the dummy head. The binaural dummy head microphone was put on a tripod, and the eye level was measured to be 1.55 meters tall. We physically positioned the dummy head with various player positions, and the physical room was fairly ideal as it was a multi-path sparse environment. There were sound-absorbing curtains to the left and to the right of the binaural dummy head. There was no hum of the AC to influence the recordings. Now I'd like to share the process we did to capture the ILD and ITD cues. A repeated sound sequence of 0.5 seconds of silence, followed by a 0.3 second pulse of white noise, then a 0.2 seconds of silence, moved in a raster scan pattern. This was a virtual sound source that moved. For the ILD, we took the sum of squares for each 1 second window and took the log of the left and right and then subtracted the two. For the ITD, we calculated the cross correlation between the 1 second windows and estimated the peak through cosine interpolation and then took the difference between the left and right. Here we have a sample of the ILD and ITD measurements from this particular dummy head position. The top row is our ground truth, recorded from the audio one would directly hear from headphones. The second row is from binaural audio playing from the two loudspeakers normally, without Xblock applied. The third row is binaural audio playing from the two loudspeakers with Xblock applied. The live recordings suggest that Xblock preserves the ILD and ITD cues, increasing the likelihood that the users will perceive spatialized audio. We see that the ILD and ITD maps generated from the audio processed by Xblock follows a more similar distribution to the ground truth compared to that of no Xblock. We also took more recordings in many different dummy head positions, those of which you can find in our paper. For our future vision of the spatial audio-enabled smart speaker system, we imagine a main speaker hub to process the virtual environment and synthesize the spatial sound. In our prototype, we utilize an Alienware M15 laptop 3.0 GHz running Unity to serve the role as the main speaker hub for the spatial sound synthesis. For headsetless tracking of the user and objects in the environment, we envision our future main speaker hub to have visual tracking capabilities. For our prototype, we utilize Azure Connects for visual tracking, which are connected to the Alienware serving as the main hub. The Azure Connect sensors accurately capture the physical space and maps what is tracked into the Unity virtual environment for the spatial sound synthesis. We use Lightbuzz's Azure Connect for Unity 3D package, which utilizes the Connect body tracking and camera SDKs. One Azure Connect tracks the user's head and body pose and maps the physical poses in the virtual space. A second tracks objects and maps the physical locations in virtual space. We route the audio output from the Alienware using jack audio to the smart speakers through the network with NetJack. NetJack allows real-time audio transfer over an IP network. For our smart speaker setup, we use a Raspberry Pi with a stereo speaker system plugged into the Pi. The Pi also has jack audio and NetJack installed. The Raspberry Pi receives the audio transported from the Alienware laptop, acting as the main hub. For future work, we plan on conducting perceptual user studies to understand how people perceive the spatialization effect provided by Xblock. We plan to explore the ear and speaker position tolerances to see how off the positions can be before the spatialization effect is ruined. Lastly, we plan to explore what types of sonic interactions we can create and see how we can improve the user experience. In summary, Xblock is a novel algorithm that preserves the ILD and ITD cues and creates spatial audio perception over a pair of loudspeakers using the knowledge of the user's head pose and speaker positions to eliminate auditory crosstalk. Auditory crosstalk can be canceled for a dynamically moving user. We implemented the algorithm via a Unity plugin. And last, we built a VR system and a prototype IoT speaker system with Xblock capabilities to demonstrate and measure the algorithm's effectiveness through quantitative study. Altogether, continued works on these IoT-enabled spatial audio systems will create a fabric of programmable soundscapes for any sounds to be placed anywhere.